everybody, and thank you for the opportunity to come and speak to you today about the challenges to performance physiology when exercising in a hot environment. The plan for this session is to talk about, first of all, the sources of heat stress on humans who are performing in a performing sport in a hot environment. I'll then discuss the environmental thresholds and outline some environmental scenarios where there's likely to be an impact upon sporting performance. And then I'll break sport down into different sort of sub-disciplines. So we will consider sprint and power-based performance, and that might be track cycling or field events in athletics. We will then consider endurance performance, and the marathon will be our representative example there. And then we'll discuss intermittent activities. That includes team sports such as hockey and racket sports such as tennis, badminton and squash. And that'll present quite a large paradigm of the activities which we know are likely to be impacted by heat stress in sport. And as well as characterising the impact and discussing the impact on performance, I'll also try and embed some performance physiology into the discussion and try and understand some of the mechanisms that are underpinning the impact on performance and physiology. And then, of course, we'll summarise that with some concluding comments. So first of all, then, to define the sources of heat stress in sport. Heat exchange in sport, and we use heat exchange to define the transfer of heat in the body from central regions such as the muscle to the periphery such as the skin, and also the external environment. It's quite a complex series of events that vary between individuals, vary between sports, and of course vary between different environments. On the right-hand side in the red bubbles are all of the sources of potential heat gain for someone who is exercising, competing in a warm or a warm, humid environment. Metabolic heat production refers to the heat produced by the body, and a human body is quite an inefficient machine. It produces about 80% heat for 20% energy gain. And the metabolic heat production is that internal generation of heat during activity that's providing muscle contraction. And that's quite tightly coupled to the volume of oxygen that the body's consuming, or the VO2 as we'll define it here. And a higher VO2 that's associated with more intense and certainly more intense and prolonged activities generates greater heat production and causes the body's temperature to rise. If we look at the external environment, the body can gain heat and sensations of thermal load from solar radiation, and this is the sun and the solar rays that are contacting the skin surface and providing heat transfer. Air temperature can also cause the body's temperature to increase, both directly. If the air is warmer than the skin surface, that will induce heat transfer. But also having a warm environment will slow the body's ability to dissipate heat. Likewise, humidity impacts the magnitude of heat that can be lost to the environment. A very high water vapor pressure, a high humidity means that the air is around the body is more saturated with water, and that means our sweat efficiency and the ability of sweat to leave the body is diminished. In some scenarios, in some circumstances, radiation as well as the solar radiation can be transferring heat from the ground or the surface, and the temperature can be warm on the surface, particularly late in the day when it's had direct sun on it for quite some time. And of course, the various clothing and equipment required for sporting performance, all this has the potential to inhibit the heat loss capacity. Over on the left-hand side in the blue bubbles are two primary heat exchange pathways for both internal and external heat exchange. So when the body is creating high rates of metabolic heat, blood flow around the body tries to direct that heat from that central location, the muscles and the exercising musculature, to the skin surface via the capillary beds at the skin surface to bring the warm blood closer to the skin. And that works in collaboration with the evaporation of sweat to liberate the heat from the body. And by sweating, we see a phase change from the liquid to the gas that causes some localized cooling at the skin surface, and then that cooler blood returns to central locations with the intention or the capacity to cool other regions. In green are the heat exchange pathways of convection and conduction. Convection refers to airflow around the body. Conduction refers to heat transfer via conduct or contact. And both of these actually play a very minimal part in heat exchange in sport. Airflow, particularly if you're not using something like a bicycle, is going to be very low, and is going to have a minimal chance to help reduce body temperature. For anyone who is running or exercising in a closed environment, this will be a very small component, and even smaller is the conduction pathway, because there is very little contact with other surfaces during sport. So to progress on, we'll now consider some environmental thresholds. I've already discussed the relevance of both temperature and humidity, and those two independent data points are often brought together to be combined into a single metric, which helps us to understand the likely heat stress impact of a different environmental condition. So there is a flag system within the wet bulb globe temperature, or WBGT index, that decides, based upon the combination of both temperature and humidity, what the risk for hypothermia, and we could infer from that the risk of performance impact is. So there's a color-coded flag system that progresses from white to green, and then green into yellow, red and black. And red and black are the most high risk for hypothermia, most severe thermal environments. And we can see from this table that whilst the flag colours of white and green present a relatively low risk, as soon as there's a progression into the yellow WBGT range, which is 18 to 23 degrees Celsius, there's a moderate risk of hypothermia, and the warning for competition is that there should be some level of caution, and to reduce the risk of hypothermia, slower paces may be observed or recommended in someone exercising. That risk increases through the red and black range, and of course with the progression in the WBGT from the mid-20s up until the late 20 degrees Celsius and even 30 degrees Celsius in some scenarios, there's the potential that cancellation of events might occur. Almost certainly at this range there'll be performance detriments. And it's important to note that different thresholds are relevant for different durations of exercise. So with running performance in mind, the chance of risk or the risk of exertional heat illness becomes greater for longer events at lower temperatures. So we can see that if it's just a 5,000 meter race, a 5 kilometer race, actually the threshold for elevated exertional heat illness risk might be just 29 degrees Celsius. But for a more prolonged event, and if we skip to the marathon, which is 42 kilometers, then the exertional heat illness risk may occur at even far greater lower temperatures, such as 21 degrees Celsius. And the third column of this table starts to indicate where we're seeing some thresholds for performance impairment. And 25 degrees Celsius WBGT is where, even in a 5,000 meter race, which might be something like 12 or 13 minutes at the elite end of the spectrum, there will still be a performance impairment occurring. So I'll now progress on to some individual sports and try to begin to characterise the impact of the environmental conditions on elite performance. And the intention will be that we'll start with athletics. And this is a really nice series of images for males on the left-hand side and females across a spectrum of running event races that we might see in an athletics world championships or in Olympic Games. And indeed, these are data from athletic events, world athletic events, And what we are seeing here is a comparison between performance in cooler conditions, and that's defined as below 25 degrees Celsius, and hotter conditions. And on the vertical y-axis, we've got the change in performance, and across the x-axis, the horizontal, we've got different events, and we can see there's a range from 100 meters to 200 meters. So sprint events progressing through the 400 meters to middle distance events, and then with 5,000 meters, 10,000 meters in the marathon, depicting our long distance endurance events. And if we have a look at the males on the left-hand side, we can see that there's an improvement in performance when the conditions are hot and they're greater than 25 degrees Celsius. And a lot of the narrative about heat stress is that it's detrimental to performance. And whilst that's true for many events and many competitions, as we'll see, there's the potential for an improvement in some shorter events in hot conditions, and we'll discuss the reasons for that. And as we transfer over to panel B, which is the female data, we can see that in both males and now females, there's an improvement in performance through the 100, 200 and 400 meter sprint events. For the male participants, there's no change really in the middle distance events, so the 800 meters and the 1500 meter track events. But as soon as the progression turns into the 5,000 meters, 10,000 meters in the marathon, we're starting to see changes in performance between 1, 2 and perhaps up to about 4% in some people in the marathon. So these are athletes at an elite end who are running slower simply because of the environmental conditions that they're experiencing. For females, there's a similar story at the 10,000 meters in the marathon. What's interesting with female athletes is the fact that even the middle distance events, the 800 meters and the 1500 meters, are also impacted by increases in environmental temperature. There's a suggestion, as we'll discuss later, that maybe females are more sensitive and more responsive to the perception of temperature, and they might actually put in place some individualized pacing in these middle distance events to avoid unnecessary heat stress, and they may have that more conservative approach to their performance that males don't demonstrate. So with firstly the focus on those sprint and power-based performance benefits and alluding to the 100, 200 and 400 meter benefits, researchers proposed that the performance enhancement of temperature might be due to either external factors, and we know that a warmer environment, hot air, has a reduced air density, or it might be due to internal factors such as local muscle temperature. The external benefits argument has been modelled quite extensively within the physics and biomechanics domain, and if we use the 100 meters as our example, in the sort of the range that we might expect an event to take place, so between 15 and 35 degrees Celsius, 100 meter performance will only vary across that range by 0.023 seconds, or 0.23%. So that's a very small component of the performance, and is going to be impacted by temperature. The variance with elevated humidity, so from the range that's realistic within sporting environments, so between 25 and 100% relative humidity, it is even less, so 0.01 seconds. So we can take the combined range of temperature and humidity and account for less than 1% variation in performance, far less than that. In contrast, the internal benefit of a warmer muscle has been quite extensively researched for quite some time, for many decades now. And by having a warm muscle, you're able to increase ATP turnover. You can increase the utilization of phosphocreatine, and both of those are critical factors in high velocity sustained muscle contraction, akin to and relevant to sprint and power-based performance. And from a neurological perspective, increase in muscle temperature increases the action potential velocity, the stimulation of the muscle fibers via that neural network. And whilst the external benefits of increased temperature within a physiological and environmental range were minimal and were less than 1%, increasing muscle temperature by exercising in a warm environment and retaining heat more effectively can lead to, and in this example we have in the red line, an 11% increase in the peak force during a 20-second maximal cycle. So a substantial, greater than 10% change in the force production that's capable, and this is depicted by the red line, relative to control conditions in the yellow line, and then various stages of cooling in the green and blue line. So the benefits of performance in warm conditions for sprinters and power-based athletes is largely derived from an increased muscle temperature. That allows us to now consider the benefits of repeated sprint performance. And whilst we've established that elevations in muscle temperature are beneficial for a single sprint performance and during initial sprint bouts, during prolonged and repetitive sprinting, there's a point that occurs where the muscle temperature increase acquiesces or diminishes relative to cardiovascular and accumulated metabolic strain. And on the figures here, what we're seeing is the red line is a hypothermic individual who's been asked to produce high-intensity sprint power event production on a cycle ergometer. And we can see for the first and the second sprint, when we consider peak power, there's an improvement in the hypothermic, the red line, relative to the control, the normothermic. But by the time this participant group are asked to complete a third, fourth and fifth sprint, actually the power production has diminished, and the recovery between the sprints, which is contingent on reducing the metabolic strain, and this is largely related to leg blood flow and the cardiovascular response, which is diminished under heat stress. We see by the third, fourth and fifth sprint that we're getting a reduction in the power produced relative to the control condition, and that's going to lead to inferior performance in competition. That was a series of just 5 sprints that represent quite high intensity and prolonged sprinting on a lab cycle ergometer. This figure depicts the impact on intermittent sprint exercise that's much more closely aligned to hockey or soccer or rugby performance using a cycle intermittent sprint test. And there are 3 traces here. The first trace, which is the blue line, and I've put some smoothing in with the blue line, shows the normal response to this intermittent cycle exercise, 40 minutes worth of cycling, similar to a half of a team sport competition. And the blue line represents the temperate environment. And that would be something like 20 degrees Celsius, which would be an optimal temperature for this repeated sprint activity. Each of the symbols equates to a 6-second sprint every 2 minutes, and if we draw our attention to the solid red line, here what we're seeing is the performance in a hot environment, and we can see for the first 25 or 30 minutes of performance that tracks quite closely the blue line of the temperate conditions. But from 25 minutes onwards to the end of the 40 minutes, we're seeing a dramatic decrease in the power output produced during these 6-second sprints relative to the temperate condition. So whilst the increased muscle temperature and body temperature is having a similar effect in the first 25 minutes, as we get towards the end of the half of our hockey fixture, then the increased body temperature is failing to recover the muscles from these intermittent sprints, and therefore there's a diminishing of performance before a final end spurt for the final 2 sprints. That solid red line was a hot, dry environment. As we look at a hot, humid environment, what we're also seeing is a similar response, perhaps even slightly improved performance for the first 25 minutes, and then that similar decay in the response occurring. And then there's that similar pattern where the performance diminishes after around 30 minutes. It could be argued that actually that the hot humid performance is decaying a little bit more soon in the 20 to 25 minute period before that characteristic end spurt as the exercise test draws to a close. If we now consider the other end of the spectrum away from sprint and power-based performance and consider true endurance performance at the marathon, what we're seeing here on this figure on the y-axis, the vertical axis, are the performance decrements, so the reduction in time, and this is relative to the horizontal x-axis, which is the relative finish time. And each of the coloured lines depicts different WBGT thresholds. Red indicating 25 degrees Celsius, orange indicating 20 degrees Celsius, 15 and 10 depicted by the green and the blue traces. And what we can see if we start with the blue trace, which is close to the optimal performance temperature, is actually for people who are competing in the range of Olympic marathon times. So the longer arrow depicts the likely male finish time in the Olympic marathon, and the shorter arrow around 140 minutes depicts a female performance. Actually, the performance decrement might be less than 1% in that time range. That time range and that temperature range. If we consider a worst case scenario, which is the 25 degrees Celsius, which might be close to what we're envisaging for an Olympic marathon the coming year, we might see up to about a 5% decrement in performance within that Olympic range. Clearly, for recreational participants who are running a time of 180 minutes, so about 3 hours, that curve is far greater, and we might see a 10 or a 12% decrement in their performance. But even at an elite level, a well-trained marathon runner, because of the environmental temperature, might see a reduction in their performance of 5%. And this is unique. This isn't unique to any one individual. This will be representative across the whole field. Whether someone is seeing a small or a larger decrease in their performance is likely to depend on their heat preparation strategy, as others will discuss at the conference. And I mentioned there that the 10 degrees Celsius might be representative of some optimal temperature conditions. Here's a cycling experimental study where participants were asked to cycle at 70% of their VO2 max and look to maintain that intensity of cycling exercise for as long as possible in a time to exhaustion or TTE model. And the y-axis, the vertical axis, depicts the duration participants were able to cycle for, and we see along the x-axis a temperature range from 4 degrees Celsius in blue to 11 degrees Celsius, the green, 21 degrees Celsius in the yellow, orange, and the 31 degrees Celsius in the red. And what we can see is this inverted U shape where the optimal temperature for performance is around 11 degrees Celsius, and that would allow the participants to exercise for 94 minutes in this data set. By reducing the temperature to 4 degrees Celsius, you reduce the performance capacity, and that's probably a response of the body's inability to exercise for longer because of VO2 being directed to warming of local tissue for maintaining performance and body warming in that cool environment. And we see a similar performance time as we increase the temperature to 21 degrees Celsius. So a reduction of 13 minutes from that optimal 11 degrees Celsius by increasing the environmental temperature by 10 degrees Celsius. As the environmental temperature increases even further to 31 degrees Celsius, we're seeing now quite dramatic reductions in the performance capacity in this time to exhaustion test of the participants, a reduction of 43 minutes down to 51 minutes total exercise time in this experiment. And this is a classical study in this field from the mid-90s that has been very well replicated by a number of researchers from a number of groups. More recently, the effect of humidity on endurance performance has been considered, and in a very similar model, a 70% of VO2 peak exercise intensity was undertaken during a time to exhaustion test, and the duration to complete the or the duration to reach exhaustion was recorded across a series of now different humidity thresholds. So same environmental temperature, by increasing the humidity, the relative humidity from 24 to 40 to 60 and then 80%, had quite a nice linear relationship between performance time. So a reduction of 8 minutes between the 24 and 40% relative humidity, a further 6 minutes, a reduction as the increase in humidity goes up by 20%, and then a further 8-minute reduction as 80% is achieved. So what we're seeing here is that both as temperature and humidity increases, we're seeing detriments in performance. And that detriment in performance is linked to a number of factors and the internal physiology of the participants. In particular, the absolute body temperature that's reached, and also the cardiovascular strain associated with that. And it's been a hot debate for quite some time whether the absolute body temperature is relevant directly for performance. And an editorial by Lars Nebo and my colleague Jose Gonzalez Alonso considered whether a critical core temperature, often stated as being 40 degrees Celsius, was the right metric to consider environmental induced hypothermia related fatigue. And the notion that 40 degrees Celsius was an upper limit for human performance where exercise would cease was based upon some preliminary work in the early 90s that identified that across a series of time trials, so this is the first figure on the left-hand side, a series of time to exhaustion tests completed on consecutive days as part of a heat acclimation model. Although the duration along the x-axis extended for the participants to reach fatigue, actually what was happening is they were still attaining fatigue at the same core temperature threshold, and researchers at the time suggested that what might be happening is at 40 degrees Celsius the internal body temperature is causing fatigue and the cessation of exercise. Another experimental work went on to consider this, and by looking at esophageal temperature as a deep body index in the second panel, whether you preheat someone relative to their control conditions or cool them down, although that might impact upon their performance time, then the reality is that they cease their exercise and they fatigue at the same temperature. But there's lots of data available from athletic populations that suggest this 40 degrees Celsius threshold is indeed a too simplistic model to explain hypothermia-induced fatigue, and that within athlete groups, 40 degrees Celsius is often surpassed in competition. And a few groups have recently demonstrated this by asking athletes to ingest a telemetry core temperature pill prior to exercise and then recording afterwards peak data. So this is some data from the UCI World Road Cycling Championships, which took place in Doha in Qatar. And depicted on this figure are individual temperature plots across a range of events, including the team time trial, the individual time trial, and the road race from the 2016 event. And what we can see is there are some medalists at a whole range of different peak core temperatures, ranging from 39 degrees Celsius right up to 41.5 degrees Celsius. And these are medalists, winners of the event, and they are able to win that event in spite of high temperatures well in excess of what we had previously determined to be a critical core temperature. Likewise, in a race walking experiment, event winners, and this is now a data set that includes females as well as males, winners were able to withstand core temperatures well in excess of 40 degrees Celsius, approaching 41.5 degrees Celsius core temperature. And again, there was a range of medalists in males and females who had core temperatures that were greater than 40 degrees Celsius, but also as low as 39 degrees Celsius. So this is indicating that the core temperature alone isn't a strong predictor of performance events. And the ability to withstand core temperatures in excess of 40 degrees Celsius is commonplace in athletes. To try and characterize more greatly what's going on during heat stress, myself, Carl James of the Institute and others at the University of Brighton did an experiment back in 2017 that asked participants to undertake 2 incremental exercise tests, ultimately to the attainment of VO2 max, and we did this in 2 environmental conditions. First in 13 degrees Celsius, and then again in 32 degrees Celsius, and that provided 2 dichotomized conditions: one a cool, close to optimal performance for this incremental test, and then again in a hot environment that simulated what we might expect high-level competition on a hot day to occur in. And across a whole panel of physiological responses that we assessed, exercising heart rate, exercising core temperature, skin temperature, blood glucose and lactate concentrations, the respiratory exchange ratio, minute ventilation, VO2 max, lactate threshold at various set points, running economy, the velocity at VO2 max, running time, and then of course sweat rate, thermal sensation and RPE. All of these metrics, so the whole range of physiological responses to incremental exercise to the attainment of VO2 max, are elevated in the hot condition. In particular, in association with the increased core temperature, which we've already seen occurs in hot environments, the most noticeable change, and one of the greatest magnitudes of change, were the exercising heart rate and the exercising skin temperatures, which both indicate that there is a direct impact of the warm environmental conditions on the skin surface, and the cardiovascular system is responding to that increased peripheral and increased deep body temperature to help mitigate against this heat stress. And as I return to work for my colleague Jose Gonzalez Alonso, he produced a series of plots which really encapsulate the cardiovascular limitations, which we believe are the strongest limitations to exercise in the heat. So on the left-hand side, as outlined by the red boxing, what we see here is blood temperature. That's a good surrogate of body temperature, increasing during a 6-minute exercise bout of high intensity. In the blue panel, the blood temperature reaches the equivalent temperature of 39, approaching 40 degrees Celsius, but rather than this occurring in just 6 minutes, the time taken to achieve that high temperature is prolonged in cool conditions to 8 minutes. If we look at the central cardiovascular responses in the figures below that, as we see in the hot condition, Q, or the cardiac output, is far greater in the hot condition relative to the cooler condition, and this is for the same AVO2 difference, or the the atrioventricular oxygen difference. What we're also noting is that heart rate is increased in the hot environment, as we saw in the warm conditions, and stroke volume is elevated, but then still diminishes as the exercise termination occurs. And this is tightly coupled to the reduction in the mean arterial pressure, the MAP, on these figures, which in the hot panel reduces greatly towards the end of exercise, and there's an inability of the body to sustain blood pressure. At fatigue, in the cooler conditions, most of these responses are maintained, with the exception of stroke volume, which is now reducing and causing the reduction in cardiac output. As we transition over to the right-hand panel, at exhaustion, we can see that minute ventilation and other metabolic responses are very similar between the hypothermic and the control condition. But the bottom panels, where we're seeing the AVO2 difference at the leg, the VO2 at the leg, and the leg blood flow, the LBF, all of those factors are more greatly challenged in hypothermia versus the control. In particular, the leg blood flow, which is governing the leg VO2 response. And what this means for the athlete is that in the warmer conditions, even though the cardiac output is elevated relative to the cool conditions, much of that cardiac output is being directed to the skin surface for the facilitation of cooling and to maximize the potential cooling of the evaporative heat loss pathway. And that means that blood flow to the exercising limbs, whilst it elevates during the early stages of exercise in up to about 3 minutes, by the time the 6th minute's been achieved, leg blood flow has now reduced past the threshold it was 30 seconds into the exercise, and now there's a reduction in the oxygen delivery, and that's causing the fatigue to occur. I've suggested that the red box here, the cardiovascular changes with heat stress, is the predominant factor, but of course an integrated system like the human body is subject to multifactorial responses, and these have been well characterized. So not only does fatigue or performance impairment occur in heat stress because of the cardiovascular changes, but this has a direct link to muscular and peripheral factors and impaired muscle function. That creates an afferent signal to change psychological factors, and that influences the neurobiology of the central nervous system and the chemical responses at the neurotransmitter level. And in association with peripheral muscular factors, that changes the blood composition, the pH, and the partial pressure of carbon dioxide within the body, and that has influencing factors on respiration, which concurrently impacts our perception of exercise intensity, as well as having a direct effect on the central nervous system. So this is a complex model, but for myself, whilst the direct effect of temperature is limited, the cardiovascular response precedes the series and this cascade of multifactorial integrated responses. To close the consideration, I'll just return to some team sports and now some more technical team sports rather than just the sprint element. And there's some very nice data from the Soccer World Cup in Brazil 2014, where comparisons were made between fixtures in high WBGT threshold, that was typically in the north of the country, compared to moderate and then low in the south of the country game match analysis. And what this match analysis observed was, whilst playing time and the distance covered by players and the number of goals per game and the number of passes completed weren't impacted directly by the temperature, there was a tendency for more conservative passing and a higher pass completion rate, and that was coupled with a greater increase in low intensity running activity and a reduction in high intensity or sprint running activity as the temperature increased. Effectively, what this means for match performance is that in warmer environments, soccer players are more conservative, they're less direct with their play, they're trying to reduce the amount of high intensity, high heat generating running that they're doing and favour low intensity activity in place of that. And this was nicely characterised alongside the physiology of intermittent sprint performance in the heat by researchers in Doha, Qatar, who asked 2 professional football teams to play games against one another, and they performed these games in controlled conditions, cooler conditions, in an air-conditioned facility at 21 degrees Celsius, and contrasted these with outdoor play in 43 degrees Celsius. And similar to the match analysis of the Brazil Soccer World Cup, high-intensity running reduced in this model, the total distance covered by players reduced, and then there was that adjustment in the playing style, so the pass success rate increased and a more conservative play was observed. And this is a football model, a soccer model, but we would expect to see very similar things happening in hockey matches, for example, also. The physiologists looked at both first and second half responses and noted that in the hot conditions, players were achieving core temperature of approaching 40 degrees Celsius again, and that was lower than in the control condition. Muscle temperatures were warm in both conditions, but even warmer in the second half in the hot condition. And whilst the heart rates were comparable, around about 160 degrees as an average, that average, which was equal between the hot and the control group, came from a reduction in total distance and a reduction in high intensity running. If the hot group had been asked to match their high intensity running and distance covered, then it's conceivable that we would see a far greater heart rate there. Muscle glycogen depletion didn't occur, so there doesn't appear to be an impact on the substrate used during footballers in the heat. And in this example, although others have shown different, there wasn't a change in the voluntary contraction of muscle or the neuromuscular properties of the muscle. Our final consideration turns to racket sports and tennis. And there's a nice analysis here from the Australian Open in Melbourne, which experiences very high temperatures and high WBGTs. And what we see is as soon as that threshold of 28 degrees Celsius, so approaching that, exceeding that yellow WBG status above into red and black categories, there's a greater increase of heat-related calls for treatment or calls for cooling devices, so players are feeling the sensation of the heat. The number of winners per unit time decreases as there's a progression through the WBGT zones by about 2.5% per zone. So the players are playing less dynamically, perhaps trying to play less winners in a hotter environment. And that's also characterised and shown by the number of net approaches, which is obviously an attacking play in tennis, which reduces by the order of 7% per WBGT zone. And in concurrence with the number of winners and approaches, attacking plays decreasing, the number of return points also then increases. So there's a more level playing field with that temperature increase. Why is that? Well, in a simulated tennis game in hot environments, in the red line we're depicting here increased rectal temperatures, increased skin temperatures, and increased heart rate relative to the blue line, the cooler condition. And again, point durations reduce, so the number of points that are less than 5 seconds long reduces in hot condition, but there's an increase in the number of points that are in the 5 to 10 or 10 second or greater range, which depicts a difference in the style of play from players. That's also replicated when you look at the individual point duration perspectives, whereby in hotter conditions, generally each point is longer, reflecting that more conservative play. Okay, so to summarise the key points here, most sports are going to be impacted by heat stress in one way or another. Our sprint and power-based performance, for example, track cycling or athletics, sprint events, we might be likely to see some improved power and performance, force production performance, equating to faster times and longer throws and more explosive jumps in those events. So there's a positive effect of temperature, and particularly local muscle temperature there. Endurance performance is quite the opposite, and if we switch completely the distance to the marathon, we see increased cardiovascular and perceptual strain, reducing the running speed, indicating slower or eliciting slower times. In intermittent activities like hockey or racket sports, there's a mixed picture where initially there are some benefits of having a warmer muscle on sprint performance, but generally over time and over the course of a match, then a slower or more conservative team performance or individual performance might be observed. Of course, with intermittent events such as hockey, there's the opportunity to roll substitutes on and off, and therefore there's a better opportunity perhaps at a whole team level to reduce or dampen the impact of heat stress on sports. If you could keep players in play who have got optimal muscle temperatures for sprinting, then that performance element may be maintained quite effectively. For the coach, for the practitioner, you should be aware that the physiological signs of heat stress include increased heart rates, increased sweating, which might have an impact upon the hydration status of the participants, of the athletes. We would see increased core and skin temperature that's relative to the environment which the person is exercising in addition to their clothing and their energetic demands. They would feel greater perceptual heat stress, and that might contribute to the reduction in voluntary force production, or if local temperature is high, the absolute force production available at the muscle for their sporting activities. And of course, all of these responses, as I said, are proportional to the magnitude of heat stress, which we again would characterize with our best tool at present, which is the WBGT. It's important to say that these are studies that have looked at pools of participants, and when we're working with athletes, we know that the individual needs due consideration. So large individual differences can occur, and it's very important to screen individual athletes for their individual responses to ensure that that's been well considered. So to close, there's lots of things that should be done to prepare an athlete for heat stress, and others at the conference will talk about that. So to identify sources of physiology impacting heat stress is the first point of call. For the sprint power-based performances, you would look to optimize muscle temperature for performance. For endurance-based events, minimizing temperature to reduce cardiovascular strain, and the sequence of events that occur at a physiological level after that is the priority. And then in intermittent activities, it's a balance between the peripheral and central temperatures to ensure performance is not unduly affected. And we've written a review, which I've highlighted here, on heat alleviation strategies for athletic performance that considers not only these sources of heat stress and the challenges to performance physiology, but also some solutions to mitigate against them for the athlete. Okay, I'll just close by saying thank you very much for listening. Thank you for your time and your comments, and I'm glad to answer any questions you may all have. Thank you very much.